Students across the world spend years achieving high computational fluency in basic arithmetic, only to hit a severe cognitive wall the moment they are introduced to formal algebra. For 70 years, the Soviet mathematics curriculum structured its instruction to avoid this exact wall by strictly dividing the work across two distinct books. A.P. Kiselev's textbook handled the pure theory, the logical proofs of why arithmetic works. E.S. Berezanskaya's companion problem collection took over the practice, detailing exactly how to use it. But Berezanskaya's collection was not a repository of rote repetitive drilling. It was engineered to test the absolute boundaries of a student's cognitive load. The text assumes the reader already understands the theoretical model. The problems exist to force the student to bend and stretch that model in extreme ways. This two-book system bridged the arithmetic algebra gap. It treated numerical practice as a structural exploration of numbers rather than the mere repetition of established algorithms. At the core of this method is relational arithmetic. This is the ability to manipulate the structural relationship between operands rather than calculating a static answer. To see how this works, we can contrast a standard modern arithmetic problem with a relational problem taken directly from the Berezanskaya text, problem 107. The modern problem on the left requires only the mechanical execution of an algorithm to find a single dead-end result. The problem on the right forces the student to track how altering one specific variable dynamically shifts the entire mathematical ecosystem. The student here is solving for a behavior, not a numerical answer. By asking how changes cascade through an equation, the text forces students to think in abstract variables years before those variables are formally introduced. Berezanskaya casts this logic in the relation between the data and results sections, beginning with subtraction. This diagram represents a subtraction equation as a dynamic balance scale. We will use it to solve problem 106, which asks how to change a subtract end to force a specific difference when the minuend has already been decreased. The student must process the first abstract constraint. The minuend is reduced by 453. Logic dictates that reducing the minuend naturally shrinks the difference. You can see this imbalance as the left pan tips upward. Then comes the second counteracting constraint. The student must force the difference to increase by 207, despite the loss on the minuend side. To restore perfect balance, the subtract end must absorb the initial loss and provide the new growth. The student combines the two constraints, 453 plus 207, to realize the subtract end must be reduced by 660. Notice that no starting numbers were provided. The logic holds true regardless of the base values. This mental balancing act perfectly mirrors formal algebraic manipulation, executed entirely through pure arithmetic logic and abstract structural reasoning. This structural reasoning extends beyond additive balance into multiplicative scaling, specifically targeting division. This visual ratio model displays a large fraction, matching the parameters of problem 348. The problem challenges the student to manipulate a quotient by altering the dividend given a halved divisor. The first constraint presented is counterintuitive. The divisor is decreased by a factor of 2. This logic relies on the inverse relationship between the divisor and the result. If you divide a set of objects into 5 groups instead of 10, each group doubles in size. Cutting the divisor in half results in a quotient twice as large. The second constraint requires the student to overcome that natural doubling to force the final quotient to decrease 50 times. To resolve this, the dividend must shrink enough to cancel out the doubling factor of 2 and apply the new reduction factor of 50. Again, the complete omission of specific integers demands purely abstract scaling logic from the student. By removing the crutch of specific numbers, the curriculum forces students to understand operations as behavioral rules of physics rather than formulas to be memorized. Problem 354 stands as the culmination of relational fluency, where multiple abstract operational rules intersect. This flowchart maps out the puzzle's first condition. Dividing the dividend by triple the divisor yields 18. The student must deduce that if an artificially tripled divisor yields 18, the true quotient must be 3 times larger, which is 54. The second condition states that if the dividend is divided by divulgent, the result is 85. By applying the commutative property of division, we know that if the quotient and divisor swap places, the result remains consistent. Therefore, the true divisor is 85. To find the missing dividend, the student merely multiplies the newly discovered quotient of 54 by the divisor of 85. Solving this requires a student to view division as a scalable fraction and as the exact inverse of multiplication. We can return to the initial subtraction prompt, problem 106, to reveal its true mathematical identity. The student mentally balanced three constraints. The minuend decreased by 453, the difference increased by 207, and the subtrahend had to absorb both. Looking again at our balance scale diagram, we can translate those exact cognitive steps into formal algebraic notation to show they are identical processes. There is a perfect one-to-one overlap between Berezanskaya's arithmetic adjustments and algebraic variable manipulation. Soviet students met formal variables like x and y with a ready-made mental model. They were merely assigning symbols to a machine they had already built. Fluency in the Kiselev-Berezanskaya model was never defined by raw calculation speed, but by relational flexibility. This historical rigor stands in sharp contrast with modern curricula that often rush students into formal algebra before this relational bedrock is laid in arithmetic. For modern curriculum designers, the directive is clear. We must stop treating arithmetic as a race to a static answer. Educators must prioritize testing the boundaries of operations, teaching how math behaves alongside how it is calculated. Rigorous foundational math design must prioritize teaching how operations behave. This ensures students understand the architecture of mathematics through its behavior before they ever memorize its alphabet.